folks, welcome to example 2. So we're going to take a look at some actual partial fraction decomposition when you have a fraction where the denominator has non-repeated linear factors. So when I say linear factor, it's something like x plus 2 or maybe an x minus 5. When I say non-repeated, the exponents on these factors are 1. So not only is the exponent on the x variable 1, the exponent on the factor is 1. So the linear part is because this x is raised to the first power. The non-repeated is because this binomial or this factor is raised to the first power. And so what we're essentially going to do is we're going to break down your rational expression, right? Denominator has non-repeated linear factors, and the degree in the numerator has to be strictly less than the degree in the denominator. And what we're going to do is we're going to break down that denominator into multiple fractions where each factor of the denominator has its own special fraction, okay? And something to take note of, if you've got a linear factor, which we are, these first examples are looking at denominators where you have linear factors. If you have a linear expression down here, you will have a constant up in your numerator. When you go through the process of partial fraction decomposition, whatever the degree of the expression in your denominator, the degree in your numerator is 1 less. So what I'm trying to say here is if I had something like x plus 2 down here, I will just have a constant up top. If I had an x minus 3 here, I would put, we tend to use different letters, like A, B, C, we'd put a different one down there. But when we get there, if you have something like x squared plus 4, a quadratic factor, you will have a linear expression up top. All right, so the degree in the denominator is always 1 more than the degree in the numerator when you're going through partial fraction decomposition. I'm going to erase this because this is coming, and I don't want to start a list just yet. So we're going to break down this fraction. So something I want you to note: we have a quadratic factor or a quadratic expression on the denominator and a linear expression on the numerator, right? Degree 2, degree 1. So as of right now, the degree in the numerator is less than the degree in the denominator. So our game plan here is to factor this denominator and then break that rational expression, right? P of x over q of x, 5x plus 16 over x squared plus 10x plus 24. Break this, that's here on the left, into individual fractions based on linear factors in the denominator. So our first attack plan is to figure out what that denominator factors into. So if I try and break this down, and let me scooch this up because we're going to need all the space we can get. These tend to take a minute. I'll look at 5x plus 16, right? And then x squared plus 10x plus 24. I need two numbers that multiply to 24, but somehow add to 10. So that would be 6 and 4. So I've got x plus 6, x plus 4. And it doesn't matter the order that you write these in. All right, so what does decomposition or partial fraction decomposition actually look like? What we're trying to do is we're trying to take 5x plus 16 over x plus 6, x plus 4, and break it into two separate fractions, one for each factor in that denominator. So I would like to break it into a over x plus 6 and b over x plus 4, where a and b are just constants, and we don't know what they are right now, but by the end of this problem we'll know. Like maybe a is a 3 and b is 2, and I don't know yet, but they're just numbers. So the idea here is we've got an equation and we've got fractions. And a lot of times it's easier to work with an equation if the fractions aren't there. So a tactic we have in math is if we ever want to knock out fractions on an equation, multiply everything by the LCD, and the LCD in this case is x plus 6, x plus 4. So what I'm essentially going to do is I'm going to multiply the LCD to the left side and to the right side, meaning I'm going to multiply it to both of these two terms. And as long as I do the same thing to the left side as the right, I get to maintain the equal sign. So this line is going to take a minute. I'm going to multiply the LCD to this term, and this term. So here we go. So I'm going to take LCD of x plus 6, x plus 4 to the left side of that equation. I'm also going to take that LCD to the right side of the equation, which means distribute it to both of these terms. So we got x plus 6, x plus 4 to a over x plus 6, and then we also have x plus 6, x plus 4 to b over x plus 4. And a lot of things are going to cancel by design, right? That was the point. We said, hey, we want to get rid of the fractions. So x plus 6 is a binomial, cancels with x plus 6, right? These all essentially divide out. And you'll take note that each denominator is gone, right? They divided out or it canceled out. That was by design. So if we look at what's left, I've got 5x plus 16 on the left side. I've got a times x plus 4 on the right, and then b x plus 6. And what we're going to do, we're going to distribute this part of the equation, and then we're going to match up things that are on the right and left side with like terms. All right, so let me move this up because like I said, we run out of space with these pretty quickly. They tend to be a lot of algebra. So if I expand out the right side, I'm looking at ax plus 4a plus bx plus 6b. And what we're going to do is we're going to line up like terms. So what I mean by that is if I look on the left side, I have a 5x. That's my variable term. And if I look on the right side, I've got ax plus bx. So even though I don't know what a and b are, I know that a plus b has to be 5 because ax plus bx has to be equal to 5x. So those numbers have to align. Maybe a is 7 and b is negative 2. Right, but 7x minus 2x would be 5x. Maybe a is 4 and b is 3. And 4x plus 3x would be, well, that's not true. Maybe if a is 4, maybe b is 1, because 4 plus 1 would be 5. I can add to 5. But the idea here is a plus b has to equal 5. And now if we line up the constants, I've got 16 on the left side, 4a and 6b on the right. So 4a plus 6b has to equal 16 because these two terms are going to align to that constant. So I know that 4a plus 6b is 16. And now I've got a 2 by 2 system of equations, right? So now what we essentially want to do is solve this 2 by 2 system. Now we can solve, let me write system of equations. We can solve it with substitution. You can solve it with elimination. I'm looking at this and I'm personally going to solve this with elimination. I'm going to multiply this top equation by negative 4 and knock out the a's. All right, so I'm going to do negative 4 times this top equation, and then I'm going to add it to the second equation. So if I multiply, and I'll just put in parentheses here, this equation by negative 4, I'm going to do my work over here. I'm going to have essentially negative 4a minus 4b is going to be equal to negative 20. And then I'm going to have positive 4a plus 6b is going to be equal to 16. So let me add those two equations together and then see what we get left with. The a's cancel by design. I've got negative 4b plus 6b is going to be 2b. Negative 20 plus 16 is going to be negative 4. And then I'm going to divide both sides by 2. So I'm getting one of mine. B is negative 2. Okay, and then if I substitute that back in here, if I know a plus b equals 5, right? If a, and can we see this on the side? I want to make sure I don't run out of room. If a plus b equals 5, that's saying a minus 2 equals 5. A is going to be 7. So I've got my a and b values now. Oops, excuse me, I knocked that out. I solved my 2 by 2 system. A is 7, b is 2, and that's going to essentially get me to my answer. So in a moment, I'm about to write a 7 here, right? 7 over x plus 6, and then I'm going to write negative 2 over x minus 4. And really, I'm going to subtract the x minus 4. So ultimately, right, and I'm going to scooch this up, and then I'm going to show you a slightly alternative way to do this. My end game answer here would be that I can break 5x plus 16 over x squared plus 10x plus 24. Well, let me put a little separation because that is pretty close. I can break that into, okay, a was 7. I can break that into 7 over x plus 6, and then I'm going to do minus 2 over x plus 4. Right? And if I ever wanted to go and check my work, I could find the LCD here, combine like terms, see if I got back to 5x plus 16. Okay. All right, but I want to take you on a little side quest. I want to show you an alternate way to get 7 and negative 2. So I'm going to go from this step here. And I want to be clear, this alternate way, both of them are totally valid. You decide which one works better for you. So if I look at 5x plus 16 equaling a times x plus 4 plus b times x plus 6, another tactic we have is we can substitute in particular values of x to solve for a and b. And let me scooch up just a wee bit more here. So what I could do here is, and I'm going to pick specific values, right? So I'm going to let x equal -4 intentionally, okay? If x is -4, 5 times -4 is -20. -20 plus 16 is -4, right? If x is -4, -4 plus 4 is 0, and this term zeroes out. If x is -4, -4 plus 6 is 2, so this becomes 2b. And if you divide both sides by 2, you get -2, right? So that might be seen as maybe a faster way of getting there. And then I could let x equal -6. I'm intentionally choosing the values that zero out these factors. If x is -6, 5 times -6 is -30. -30 plus 16 is -14, all right? If x is -6, -6 plus 4 is -2. -2 times a is -2a. And if x is -6, -6 plus 6 is 0, and b times 0 goes away. If I divide both sides by -2, what are we getting? A equals 7. All right, so sometimes it's faster to do this method, and sometimes you have so many repeated factors, it's faster to do the system of equations. But I did want to show you both. All right, thanks so much. Bye.